Hello, everybody, and welcome to PyCon Sweden 2021. And this is the software track, and I have the pleasure to introduce you to Harsh Mittal, who will present to you his presentation. Just a short introduction. So, Harsh, he is currently working with as a computer visions engineer at Asteria Aerospace and is working on developing advanced capability drones. He will present about building custom robot in ROS. Welcome, Harsh.
Yeah, thank you.
And the stage is all yours.
Okay. Hello, everyone. I am Harsh Mittal, and to give you a brief introduction about myself, I'm currently working as a computer vision engineer in the field of robotics, and I'm deeply passionate for the field of robotics and making autonomous drones. I've also had the opportunity to work in multiple defense-based startups, and in my free time, I also like to create YouTube videos, write some blogs. So you can surely check me out on all the different platforms like YouTube, GitHub, Medium, and LinkedIn. So let's get started with the talk. Why are we here exactly? Well, to give you in simple words, like simply creates our own robot. Right? I don't think I need to explain why exactly you should get into robotics. Robots are generally like they have already become an integral part of our day-to-day life, and it'll continue to be so. And now with all the resources that are freely available online, it is a lot more easier to get into this field. With this present on this presentation, you can see like I have shown different examples of the bot that have been created using ROS. So today we'll learn how to create one. At least to get you started, you can do this simulation using ROS. So the ROS itself is a very wide topic, and it will be very difficult for me to, tell you everything during this duration. So I'll try to squeeze in all the major details to just get you started. On the screen, you can see the bots that we'll learn to create. So we will create a two-wheeled and a four-wheeled bot, that is Atom bot and a Beta bot. So you learn how to actually create this bot, add sensors to it, and change their physical appearance. The method that I'm showing over here, it's not limited to just for the wheel robot. You can actually use it to implement any sort of robot that you can imagine. So those of you who don't know what exactly ROS is a robot operating system. It is kind of set of different software libraries and tools that can help you build all the different kinds of robotic application. So this project is completely open source, and there are a lot of free algorithms that are actually available online that you can use to create your own projects. To give you a brief idea about all the different ROS versions that are there. So if you have Ubuntu 18 installed, then you can use ROS Melodic, and if you have Ubuntu 20 installed, then for ROS 1 you can use Noetic, and for ROS 2 you can use Foxy. For this particular demo, I'll be using just ROS and will not be focusing on ROS 2. To read more, you can check out the distribution link on the ROS wiki. Okay. Now, once you have installed ROS properly, I'll give you a brief idea about the complete architecture of how all the code is present and what are the different components that we'll be using. Right. So for the root folder, you have your Catkin workspace, which will basically contain three folders that will be source, build, and devil. So source contains all the source code related to your Catkin workspace. Build will have all the cache and other intermediate files, and the devil is basically the development space where all the build targets will be placed. Now, in the source folder, you have different packages. A different All these packages can be like set of bots or a different set of algorithms that you want to include, right? In the package itself, you have your cmake list, which will be your build system. Then comes your package.xml file. So this file will basically define a lot of different properties like your package name, its version, authors, maintainer, and majorly what are the different dependencies that you actually require in your catkin packages. Then there are different folders for script, custom messages, services that you want to include, then include source folder, and finally your launch folder. So launch folder contains a launch file which will help you run multiple ROS nodes at once. So what exactly is this? I'll like cover in later slides. So first understand how ROS actually works in the background, right? So you start a ROS master, and you have all the different nodes. So all the data the data exchange that takes place is using a PubSum model, right? So each program that you runs is a node, and node will either be a publisher, that is it will send data, or a subscriber, that is it will consume data. So different topics can actually be used for different types of data. For example, if you have a robot and you want to detect obstacles, then on one node you can have the robot running, where it will be publishing your camera image data on a topic that we had defined. For example, camera underscore data. Meanwhile, on another node, we can subscribe to that topic, that is camera underscore data, and then retrieve it to detect obstacles. Now, in all of this, where exactly we'll be using Python? So Python we'll be using to create, first of all the different nodes. So basically processing our data, and also to generate URDF files. So this topic I'll cover later. Okay, some of these two are one of the basic tools for ROS that we'll be using. ROS is the visualization tool. So anything related to like camera, sensor data, or even the robot itself, any type of map that you want to see, you can visualize it using ROS. And Gazebo is the 3D simulation tool. So anything like from the complete robot to all kinds of physics that you want to simulate, you can actually use Gazebo for that. Now let's start by creating our first robot, that is Atom. Now the source code is available on my GitHub. The link I have also provided, so you can check it out. I'll not be able to discuss all the complete code, but yeah, I'll give you the brief snippets, and we'll discuss the major points. So this is how the basic architecture of the things we'll set up, right? So first of all, you'll have your launch file. In the launch file, you have your world file and your robot description. And in the world file, we'll first write an empty gazebo world, and we'll give the initial camera angles at which we want to initialize our world. And in the robot description, we'll add our robot URDF file and the joints and transformation values. So one by one, I'll cover each and every layer and describe you how things will actually work and what they are actually. So let's start with the launch file. Launch file provide a very convenient way to start up multiple nodes and a ROS master. It along with it, it also help us initialize some of the initial parameters that we might want. So the format of this particular file is XML. So over here you can see, for running a bot, like you need all the different things. For example, in one terminal you might want to run the camera image subscriber, and on one terminal you have to open to control basically the robot. So everything can be controlled using this launch file. In the code itself, you can see I have initially given all the different parameters that I'll be using, that is to spawn the robot, right? Next, I have included a file, that is robot underscore description file. So this line will basically include this file from where we have given all the different robot information. So let's see what is exactly there in this particular file. Uh, Over here, using this line, we'll first convert our Zacro code into URDF. To give you a brief idea, what exactly this means is everything related to our visual aspect, our collision aspect, and all the different robot aspects will be defined in this particular files. And by default, everything is the file is used as URDF. So we'll discuss how exactly you can write Zacro as well as URDF files later in the slides. Okay, next we'll add two nodes. So the first one will be the joint nodes, and the other will be the transform values. So this is basically the TF values. These are required to have transform data values coming in from the source and can be used in some other aspects. So for example, if you have lidar data coming in and if you want to use it with respect to some robotic arm, then these values will actually help you transform those data, right? Next, in the launch file itself, we'll add the world file. So how exactly we can write it, we'll discuss later on. The final step would be to actually spawn our robot, right? And this is an optional step. So if in case you want to start the ROS from the launch file itself, then you can add it, else you can remove this line. Now let's come to our world file. So what exactly is a world file? It helps us initialize the world elements in the Gazebo environment where our robot will be spawned, right? So over here, I have just added a basic ground plane and sun to give it a light source. And also I've initialized the camera angles. If you run the launch file now, then you'll get an empty world in Gazebo. And since we have not written anything in anything for the URDF and the Zacro file, no robot is shown actually, just an empty world. Let's start with the URDF. So URDF is the Unified Robotic Description Format. It is an XML file which ROS uses to describe all the elements of a robot. Now it has several disadvantages. Like if you use directly the URDF file, the first will be it's very inflexible. Next, it's not universal, and we cannot specify things that are not robot. So if you want to add some obstacles in front of your robot, unless and until it is of type robot, we cannot actually describe it using URDF. So what are the other alternatives? First is using Zacro along with URDF, or second is STF. So STF format is basically used by the Gazebo to add any of the elements and describe anything. So we'll also discuss the STF files later. Now comes our Zacro part. Zacro is basically the scripting mechanism that adds that allows modularity and the code reuse when defining a URDF model. Now, the first thing you might have observed in the robot description file, this particular line was added to basically convert URDF via launch file. So this is happening during runtime. So whenever you launch the URDF file, it will automatically convert your Zacro to URDF. In the Zacro file, the first thing that we do is define all the different properties of the robot, like its name, its mass, then its the robot wheel size, etc. Okay. Now everything in the Zacro file is added as a link. So each component, for example, if you want to add a box or chassis, then you need to add it as a link. So over here in the example, I have shown you the code for a chassis, right? There are three things that we need to add in a link. First will be inertial. So this is basically the physical properties, for example, your inertia, mass, etc. Next come your collision properties. So collision elements are for simulating collision in the Gazebo. And finally your visual. So this is basically your robot visualization. Similarly, the way that I've added links for chassis, we need to add for wheels, camera, and LiDAR. So for that, you can check out my GitHub repo, like how exactly you can add those. Next, what we'll do is we need to connect those links. So for each link, there can be two types of joints in this example. So it can be either fixed or continuous. So for components like cameras, LiDAR, etc., which will not be moving, I have added a fixed joint. And for wheels, I have added continuous joint, right? So you need to specify the parent. So parent in our case will be chassis, and the child will be right wheel back that I have defined over here. Next comes basically adding color just for the visualization part, right? The final thing would be actually adding different plugins. So just adding wheel itself will not tell how to actually simulate it. So for that we need Gazebo related plugins. So for that we'll create a separate file that is atom.gazebo. In this particular robot, we'll be adding three different plugins. First will be for wheels, second for camera, and third for LiDAR. So for wheels, there are actually two types of open source plugins that are available. If you have a two-wheel robot, then you can use differential drive plugin. And if you have four-wheel robot, then you can use skid steer drive. For Atom bot, we'll be using skid steer drive plugin, right? So this is the code for actually using it. You need to specify all the different links for your wheels along with all the initial parameters that you can find in the repo. Next, we'll be adding camera plugin. So there are a lot of different properties that you can actually control. You can control the width, height, format of the video frame that you want. You can also control the FPS, FOV. Make sure the topic name is correct. So this is the same topic name that you'll be using later on when you'll write the Python code. Similarly, we'll write it for LiDAR as well. In case of LiDAR, we'll also be adding noise just to give a realistic look. So noise can also be added in other plugins as well. You can check out at ROS wiki. Now, finally, we'll be testing our bot. Okay, for in another terminal, we can also run this command. So this is the teleop keyboard library that is also written in Python. You can check it out on GitHub. This is how our bot will actually look like once we have added all the different elements. And to give you a quick demo, this is how things will be running. You can see there's a camera feed also coming, so we can see the obstacles that are present in front of it. And using the terminal, I am able to control the bot properly. Um, on the left hand side, you can see that is the ROS tool, which is helping us visualize everything. Now, this process was fairly complicated but was very essential. Now, I'll show you a very easy way to actually develop your robot with all the type of things you can imagine. Right. So for this, I'll be using Fusion 360. So there are other designing software as well available. You can use them as well. Right. Uh, so this is the beta bot that I have created. Now designing in Fusion is comparatively easy, and you can check out some of the tutorials online for doing that. Over here, I have designed a two-wheel robot with a caster wheel. I've also added a box for camera, LiDAR, and a Raspberry Pi. Okay, in this slide, I have added all the joints as well. Now I'll explain you what will be the format or the workflow of actually doing it. So the first thing will be designing your bot. You have to create the complete bot according to your own requirement and add components like wheels, shaft, cameras, etc. Remember, wheels should be added as a new body, while shafts can be part of chassis only. While adding external components, like Raspberry Pi, make sure you have the origin same. And I can show you over here. So this is how everything will be there, right? Once you are happy, you need to basically convert all the different bodies into components. So over here, you can see on the left hand side, all the different parts are now converted as separate components, right? Once that is done, then you can add joints according like whether it should be fixed or continuous. Then finally, we'll be using open source library, that is Fusion to URDF. This particular library is also written in Python to basically convert your design into URDF files. Along with URDF, it will also create launch files and all the different files that world file as well that we have discussed in previous slides. Okay, now if you launch it, this is how our bot will look like. So by default, the color and everything is set to default, that is silver. You need to make all those different changes, like add different colors according to your own need. Then you need to also specify the friction values. So for example, for wheels, the mu should be close to 1000, and for the caster wheel you can keep it to 0.01 or 0.02. Then you can also add all the different plugins. So all this was already discussed in the previous slide of how you can actually do it. uh, One thing to make sure that you copy from the Fusion 360 is your wheel separation length and your wheel diameter, because you need to specify that in your differential drive plugin properties. Okay, so this is how a bot will look like with the LiDAR running, and you can see the rays coming out of it. You can turn it off if you don't want, but still you'll get the data. Now let's finally move our bot. So this similar commands will be actually used to run our bot. So this is the specialty of ROS. You can use your previous packages that you had already built to use in all the different kind of robots that you have created. Right, in the ROS you can visualize it properly. In the right hand side corner, you can also see with red dots the LiDAR data is also coming in for the obstacles that are present in front of it. Now, finally, what we'll do is we'll get our video feed in the Python and use it to process it. Okay. So till now, we have covered how to create a bot and how to send data. But now we'll actually need a process to handle it properly. Now, in Python, you cannot use the ROS image directly, because the format is different in OpenCV and the ROS image format is different. So for that, you need a CV bridge to basically convert ROS image into OpenCV image. For that, you'll also have to add some additional dependencies in your package.xml file. Right now, in the main function, we'll first initialize the show image class that we'll see in the next slides. Next, we will be initializing a node, right? And keep you can keep the name whatever you want. Right now, I've kept it as image underscore converter. And finally, what we'll do is we'll do raw spin. So this will prevent Python from exiting the code till the node is closed. Now, in the show image class, we'll first initialize the CV bridge, and then we'll subscribe to the topic where we are publishing the image. So this should be the same as you had described in your atom.gazebo file. Uh, Now, the subscriber function also requires a callback function, which will be called once the new data is published. So this is all taken care by the ROS master. As soon as the new data is received, we'll basically convert our ROS image into CV image. And I've just added a circle over the image for basic image processing. And finally, we'll display our image. If you run this particular node, then this is how the things will be there. In the background, you can see I'm running the Gazebo simulation, and I have placed an ambulance in front of the robot. And in the image window, you can see from this side, I can clearly visualize the complete ambulance. Now, what we'll do, we'll publish this image back as a different ROS topic. Okay. So over here, you can see I've added the code for publishing, and the node name will be image underscore topic underscore two, right? Again, what we'll have to do is the last step will be to converting the OpenCV image back to ROS image, so that other ROS nodes can actually use it and we can visualize on RVS as well. Okay, so this was how, like, everything to be done on the Python side. You can actually explore more of it later. I'll also briefly tell you how you can actually use HDF files. So it is fairly similar to what we had written in Zacro files. Like, you'll add all the links, joins, and plugins. Like, you can read more on the link that I have given. The code is also present on my GitHub, so I've created a separate launch file which will include the model directly. Here you will observe the skin of the bot is slightly different because I have added a material. So if you provide an PNG file, that can be actually used to wrap around the bot, and you can check out the code online to understand it better, right? Okay, this is how our bot will look like. Now, for the final conclusion part, according to me, like, the best way to approach and to create your robot will be first using 3D designing software. So in my case, I have used Fusion 360. You can use other software as well, as long as they provide some sort of libraries to basically convert your code from like, convert your design to URDF files, like I had shown you previously, right? So once you have your design ready, you basically convert them into URDF, and this is how our bot will look like. Once you have this bot, then you can specify all the different parameters that you actually want. So, like, all the physical appearance and the physics properties, then all kind of plugins that you want, and finally, this is how your bot will look like, and you can use it for any sort of purposes. And then you can create all the different nodes either using C++ or using Python to basically process your data and generate visual insights from them. These are some of the reference link that you can refer to have better understanding and just to get started in ROS, Gazebo, etc. So Yeah, thank you so much. This is it from my side, and this is the project link that you can refer for all the codes that I have discussed, and you can reach out to me at any of the platforms. And let me know if you have any other questions regarding the talk. Yeah.
Thank you so much, Harsh. So I have a question. How big is the step from working with the Gazebo and simulation to actually deploying to like a Raspberry Pi and running for real?
Okay, so this is the thing with ROS. Like the code that you have actually used for the simulation, you can simulate the same thing in Raspberry Pi. So all the different libraries are already present, like they are supported in the Raspberry Pi itself. You just need to install ROS. So in that case, what will happen is your master and client will be on different systems. So for example, either you can make your Raspberry Pi as master, or you can create your laptop as master. Then all you need to do is basically exchange data, right? So once you have those data in it, then the same plugins that I'm using in Gazebo, you can use it for your Raspberry Pi itself. And on the Raspberry Pi, and you just need to mention all the GPIO ports, all the actuators that you are using, and in that sense, you can very easily use them.
Okay. Can you also like port back get back data into the simulation from if you run it on the real hardware and like see the real I don't know the
Yeah.
data that you got for real?
Yeah, so there's one thing called ROS pack, right? So all the different data that is coming on all the different topics, you can actually record them. So it will be done real time, and once you have that data, and it will be collected in a single file. So you can basically send that file to anyone who wants to simulate that, and then they can basically run that particular ROS pack file, and it will behave like it was an actual hardware who was sending all those data. So it can be actually used for all sorts of simulations. So this is a common practice that we actually use while creating our drones and for testing them. So if you have some data that you have recorded, while testing your drone, then you can see where the error was there by simulating in Gazebo to have better insights.
Okay. Hmm. And another question from my side: like how many sensors, etc., are there support for? Is that a limit in ROS or what?
Okay, so by default, like there are a lot of different sensors, or you can say plugins that are available. I don't have the link right now, but somewhere in the slides, I think I had mentioned like all the different sensors that you can include. But if you want some custom sensor, that is also that you can create. So you can create your own plugins as well as you can create your own node, right? So all you are doing is collecting those data, and then you are publishing it over a topic. So that is something universal, and other nodes as well can use that data once you have decided, okay, what will be the topic. And if you want some custom message also, like if you want to send the data in some custom format, so that is also something that ROS can help you with, and you can do customize everything in ROS.
Okay, thank you. So we have a comment from Helio saying it was a great talk. So and I agree. So thank you so much for presenting here at PyCon.
Yeah, thank you for having me. It was a great experience. Yeah.
And hope that everybody will follow the rest of the talks for the day and have a great day. See you.